Okay, so let's look at a little bit more of an advanced problem. A sled and its rider are moving at a speed of 4 meters per second along a horizontal stretch of snow. So we're not going uphill, although when I took the picture it was a little crooked, but let's assume this is horizontal, as shown above. The snow exerts a kinetic frictional force on the sled so that the sled slows down and eventually comes to a stop. The coefficient of kinetic friction is 0.050. What is the displacement x of the sled? So you'll notice that we've been given an initial velocity, v naught of x. We've been given a final velocity, right? The initial velocity here is 4.0. Sorry, before I move on, meters per second. The final velocity, they're just calling Vx, and that's equal to 0 meters per second. And they're giving us some displacement, right, x. This should be screaming out for a kinematic equation, right? So the one that we're going to use here, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in x. I'm calling it delta x just for consistency's sake here. You're used to me writing v final squared, but vx squared is also appropriate. All right, we know everything except for a. Right? If we just had a, we could solve this. And they didn't give us a. They gave us a coefficient of kinetic friction. So we're going to have to somehow get a from that information. Let's give that a shot. So first things first, free body diagram, right? This is a force problem. So we've got the sled rider. Let's look at the forces that are acting on them. The force of gravity is present. Right? The normal force is present. Normal force, okay? That's an N, trust me. And then we've got the force exerted by friction. This again, friction force here. Friction force. Okay. There's no force pushing it, right? It's just got an initial velocity. We know that the friction force is equal to some coefficient of kinetic friction here, mu naught, or just mu k, times the normal force, right? And we know that we can get the normal force because it's not moving up and down in the x and y direction. So let's sum the forces real quick. Sum of the forces in the x direction is equal to what forces are acting on in the x direction, right? It's just the friction force. So that's equal to the friction force, capital F, right? So we can figure that out potentially. Now, some of you may have noticed something already. They never gave me the mass of the sled rider. So you might be telling yourself, Mr. Woodard, this problem is unsolvable because in order to find the normal force, we're going to have to find the gravitational force. In order to find that, we know that the force of gravity is equal to mg. I know I jumped some steps ahead, but some of you guys may be panicking. Don't. We'll see in just a second. We don't need the mass. So this is the sum of the forces in the x direction. Let's look at the sum of the forces in the y direction. Okay? Some of the forces in the y direction are equal to the gravitational force and the normal force. We'll start with the normal force, right? Plus negative of the gravitational force, since it's opposite. And we know that the gravitational force is equal to mg. Okay. So I want you to pause the video for a second and see if there's a way to figure this out without the mass. Okay, so now I did not pause the video and figure out if this thing is doable without the mass. I'd already worked it out ahead of time, so don't think that I paused it. Okay. What's going to happen, guys, the mass is actually going to cancel out of this equation if we do it carefully. Recall that the acceleration in the x direction, we can find that. I haven't written the acceleration yet, right? But we know that that's ultimately what we're going for, the acceleration, and it's just in the x direction. This should say x acceleration here. The acceleration in the x direction is equal to, well, the sum of the forces in the x direction divided by the mass, right? That's Newton's second law. The sum of the forces in the x direction divided by the mass gives you the acceleration. We're more familiar seeing it this way, right? But I can rewrite it. So that's our acceleration in the x direction. And we know that, well, the only force in the x direction is this one. So let's plug that in. Acceleration in the x direction is equal to the friction force, right, over the mass. And we said that that's equal to, the friction force is equal to mu k times the normal force. So let's plug this, right, into friction force. So mu k times the normal force, sorry, my vector hat goes here, not over the end, over m is equal to the acceleration in the x direction. Maybe we're seeing it now, how mass is going to cancel out. And we said that the normal force, well, we haven't said it yet, but we know that if we go back down here, sorry, I kind of am jumping all over the place, but if we go back down here, it's not accelerating in the y direction, so this is all equal to 0, which means the normal force is equal to the gravitational force, right? So you can move the gravitational force over to this side, and you'll get this. So I can plug gravitational force in there, and we already know gravitational force is that, right? That's not the answer, I'm just showing it off. We know the gravitational force is that, so I can plug mg into the normal force. So acceleration in the x direction is equal to mu k. Man, that's a bad looking k. Let's get that fixed before we move on here. Hopefully the whole program doesn't crash now. Okay, mu k, better. And the normal force is mg over, and we've got an m in this, right? So notice the masses cancel out, right? So acceleration in the x direction is equal to mu k times g, right? And now we can plug that value into here. So let's go ahead and calculate that. Mu k was 0.05, so acceleration in the x direction is going to be equal to 0.05 times 10 meters per second squared. You can plug that in, although we need to not get in a bad habit. Let's plug it in symbolically first. Some of you guys probably are throwing up in your mouth when I said that. But let's plug it in symbolically. So forget I put the numbers in just yet. If you have it written down, you don't have to cross it out. We'll do that in a second. Let's put it in symbolically. So I'm going to flip back and forth on the pages because I'm running out of room, I think. No, I might be able to write it here. So Vx squared is equal to V naught x plus 2. And A, we just said, is mu kg, or coefficient of kinetic friction, times g. So mu kg times delta x, right? So solving for delta x, we get that we can move v naught x over, so vx squared minus v naught x equals 2 mu k g delta x. We're still solving for this guy, right? Delta x. So vx squared minus v naught x over 2 mu k g equals delta x. Now we just have to plug numbers in. So let's, I wish you would let me copy and paste that on the next page because I really am starting to run out of room and this is getting real jumbled up looking. Let's write that on the next page. So Vx squared minus V naught x squared over, is it 2 mu kg equals delta x. And in that problem, Vx was equal to 4 meters per second. 4 meters per second squared minus 0. Oh, I've got them backwards. That's the problem when you try to go for memories. You can get them back. When you try to go for memory, you can get it backwards, right? It starts with a velocity and ends with no velocity. So 0 minus, and that's squared, doesn't matter though, 0 minus 4 meters per second squared over, this has units of meter per second, but it doesn't matter because it's 0, 2 times mu naught was 0.05, so 2 times 0.05 times g, which is 10 meters per second squared. All right, so that gives us 16 meters squared over second squared divided by 2 times 0.05 is equal to 0.1, I believe. And then times 10 is going to be equal to 1. So all of this stuff turns into 1. Let's make sure that Mr. Wood is not talking nonsense. 2 times 0.05, right, times 10. So that all goes to 1. So going back to here, you're going to get a value on the very bottom with units of meters per second squared, but 1 meters per second squared. That cancels with that. Right, second squared goes away. And then meters cancels with the squared here, and we get that the displacement delta x is equal to 16 meters. Okay, that's the answer. I'll see you in the next video.